Hi everyone, welcome back to my math teaching channel online again. So in this problem, we will continue with the chapter 4 of my introduction to calculus course. And still we're using the application derivative. Now, so far I have shown you about 4 to 5 problem or 6 problem. And you see that none of the problem are similar or look the same, right? So we have a set of very variety of, of problems, and none of them are look the same. So I found this chapter is so interesting because we have derivative apply in geometry, in physics, in chemistry, in economic. I haven't shown you, I didn't even have time to show you the problem in finance, in economics. But so far, we see that we apply in geometry, and none of them are the same, right? So the previous one, we were drawing about the shape of the trough, the water trough, and now three-dimensional, right, shape. And now we draw about a different problem. So I found like this chapter is very interesting, and that's why I try to show you as much as to solve the problem, derivative problem, see how interesting it is. Okay, so let me get into this question right now. So let's read together. A man 2 meter tall walks away from a lamppost whose light is 5 meters above the ground. If he walks at the speed of 1.5 meters per second, at what rate is his shadow drawing when he is 10 meters from a lamppost? So in this problem, we have to pay attention into the light shine on him to make a shadow. Is the shadow in front of him or behind him, right? So if he walked, the direction is important. If he walked towards the lamppost, then maybe his shadow changing. But he walked away from the lamppost, then his shadow will be in front of him. So in this case, because he walked away from the lamppost, so his shadow in front of him. So I draw an image in that this is the lamp with the height of 5 meters, and this is a man with the height of 2 meters tall, and he walked away. So this arrow show direction of his walking, right? Let's say if he stand right here, very close to the lamppost, right? Let's say if he stand right here, right? So he will have a shadow, and the light shine this is the light of sight, right? The light of sight from the lamppost to his shadow, right? So this is the light of sight from the lamppost to his shadow. So let's say if he stand right here, from his feet right here, right? We have a long shadow, right? We have a long shadow. Then as long as he walked toward, he walked far away from a lamppost, then his shadow is getting smaller and smaller, right? I think so because he stand right here. So his shadow is long, right? His shadow long if he stand right here. As long as he walk far away, then because the distance from the light and the distance from the light and him is getting changed too, right? So this is the small triangle. If you walk up to here, and then getting a big triangle. Okay, so I'm not sure that. What do you think? Do you think that his shadow will getting smaller as he walked away, or but in here they said drawing his shadow drawing. Now I'm not sure about this, but for me, I think that his shadow from here to here should be longer, right? Then when he walked away, his shadow getting smaller. That's the scenario I think. But because they use the word drawing, so it confused me. But after we solve the problem, we will know his shadow getting smaller, smaller, or getting bigger and bigger if we solve correctly, right? So let's see. Okay, now we know that the question asks for that. So let's write out what the given information, right? Given, what do they say? Given the height of the lamppost, which is the capital height, equal 5 meters. The small height of the man, right, is a man, equal 2 meters. And what else do they give us? They ask for the rate of change right at the point where he is 10 meters from a lamppost. So the D distance, right, the D distance from him to the lamppost is 10 meters. That's what they've given us, right? So this distance D from here to here, let's say from here to here. So the D and D equal 10 meters. That's what they asked for. Okay. Now, you have to know that what is the fixed variable and what is the change variable. Now, all of this information is a fixed variable, right? A fixed information, fixed data, right? Fixed data, no change, right? What is changing? The change is variable, right? Which is the unknown thing we don't know. And what is the unknown thing we don't know? The distance, how far he walked from the lamppost, right? The distance from here to here. If he walked up to here, we call this the distance. If he walked up to here, then from here to here is the distance. So this distance keep changing, right? Keep changing. So let we call that as let x be the distance. And of course, the distance is variable because we don't know how far he walked away from the lamppost. And we just call it at an x distance. Okay, so let's x be the distance between him, wherever he is, right? From the lamppost, So let's call this is the x distance, right? And I mark here, from here to here, we call this the x distance. So his walking is the x distance, right? So now we know that we want to measure from here to here, which is 10 meters. So anytime he walk up to here, this distance will be changing, right? So this distance will be changing, and this distance from here to here, right? This distance changing, and that equal 10 meters minus with x, whatever he walk up to, wherever he walk up to, right? So 10 minus x. So 10 minus x is this distance from here to here, right? And this distance is keep changing, right? So this distance is 10 minus x. So it depends on how far the x is, right? But we know we want to measure from 10. So the distance between him, if he's here, the distance measured from 10 meters will be 10 meters long from all the way from here to here, subtract with the distance x here, right? So that's how we know. Now, what else do they give us? So they give us this stuff, and they give us his speed, and his speed is where he walking, right? So he walked at this x, right? And then he walked up here is another x, like longer, right? So given dx over dt equal 1.5 meter per second. So this is what they tell us, right? Right here. His speed of walking, and he walked horizontally, right? X distance. So dx over dt is 1.5 meter per second. What is the question? The question asks, what is the rate of change when he's 10 meters from the lamppost? So the question asks for ds, which is his shadow, ds over dt. That's the question. Okay, so now we know what they tell us and what they ask us. Thus, I need to know two things in the word problem. I need to know what data they give us, they tell us, what information is that, and what is the question. That's, I only need two things, right? And I have to write down, okay? Now, let's solve this problem solution. Now we have to, based on the diagram, and try to establish a function so we can solve for it. First of all, we notice that our function have to involve what? Shadow, right? And have to involve the x variable, the distance, and maybe have to involve this information as well. So let's find out. So to establish the function, we want to find ds over dt, right? This is what we want to know. So to find ds over dt, we have to establish a function with have an s in there. So if you're watching the big triangle here, right, and a small triangle, and he walked from here to here, his small triangle changing. At this point, his small triangle is this part, right? When he walk up to here, the triangle he getting smaller and smaller, right? So I believe that what I assume is correct, because if the triangle involves the shadow, if the triangle getting smaller and smaller, it shows us his shadow also getting smaller and smaller. So they shouldn't say growing, they should say decreasing. But let's see how it works, okay? So you see, if he up to here, then we have a big triangle, right? We have here, then this triangle getting smaller and smaller. So this triangle, the piece from here to here, this triangle is including involve his shadow is getting smaller. So let's find out. So we know that we can use a ratio, right, to establish our function. We have a big triangle, or we have a small triangle over a big triangle. We can establish the ratio like that, right? So we have small triangle over big triangle. So let's establish the ratio like that, okay? So what is the small triangle? So from here to here is his height. His height never changed. That's fixed, right? So 2 over his height over his shadow, right? 2 over shadow will be equal. The height of the big triangle is the height of the lamppost, which is 5, over the distance from here to here, right? This distance stands for his shadow, right? So will be equal small s, adding with, so 2 over 5 equal 2 over 5. Okay, but I'm going to have to write again, sorry. So we say the small triangle, the ton over the ton equal the distance x, small one over big one. So 2 over 5 equal s, which is his shadow. This distance is his shadow, right? Shadow over a big one here, the whole length from here to here. And whole length from here to here is divided by s, adding with 10 minus x, right? Because the whole length here is s, right? This is s, adding with 10 minus x, right? 10 minus x. So depend on where he stand, right? This distance is 10 minus x. From here to this point, if he walk up to here, is 10 minus x from here to here. If he walk up to here, 10 minus x is from here to here. If he walk up to here, 10 minus x is this one small thing from here to here, right? So 2 over 5 equal s over s plus 10 minus I. It seems that this is the function we established, okay? So let's do cross multiply. So we have 2 times with, this time this, s, adding with 10 minus x equal s times 5 is 5s. S stands for shadow, right? So now distribute inside, we have 2s, adding with 20 minus 2x equal 5s. Solve this equation because we have two like term here, 2s and 5s. So I'm going to move the 2s over the right hand side. So I have 20 minus 2x equal 5s minus 2s. And therefore 20 minus 2x equal 3s. So at this point, I already established an equation like this. You see our function. So now we're going to do derivative both sides, right? Derivative both sides. We have derivative 20 is 0, minus derivative 2x is minus 2. And don't forget, you can put dx over dt right beside it. Equal derivative 3s is 3 and ds over dt. So now we're going to substitute whatever we know in here. So we have minus 2 times with dx over dt is this one, right? The given information. He working with this speed, with this rate. So minus 2 times 1.5, which is we substitute this, right, by 1.5 equal 3 ds over dt. To solve for ds over dt, we divide both sides by 3. So that cancel. We get, so I'm going to do a little bit here, right? So I will get minus 2 times 1.5. So the same like minus 2 times with 3 over 2. Right? 1.5 same triple to divide by 3 again. So the 2 here cancel with 2 here. We have 3 divided by 3. But this is minus, right? So minus 1. So ds over dt equal minus 1 meter per second. So yes, anytime he walked away from a lamppost, his shadow decreasing because the negative sign. See that? The negative sign decreasing by 1 meter per second. So this is decreasing instead of saying growing. Okay? The question should state decreasing. So his shadow will decrease by minus 1 meter per second. So you see that each question, we have a different way of solving the problem. We have to look at the diagram, right? And we know this is small triangle over a big triangle. So we pair the ratio and we solve for the variable. So we solve for the variable and we take derivative of the function. And that's how we answer this question. So now we can say at what rate? So we can say his shadow, right? His shadow, D, will be decreasing at a rate of 1 meter per second. That's our answer. Okay, so let's summarize what we're doing here. To solve this derivative problem, I'm going to write out what information they give us. So I say given the height of lamppost is 5 meters, the height of a man is 2 meters, the distance D we want to measure the distance D at the point of 10 meters away from a lamppost. So from here to here, 10 meters. And we want to identify which is the changing variable and which one is fixed variable. So this is fixed, this is fixed. The x distance is the changing variable, right? Because he will keep walking at the x distance. So we realize that if he walks from here to here, then the distance is always 10 minus x, regardless x getting bigger and bigger, right? So distance here getting smaller, as well as his triangle getting smaller, and his shadow from here to here getting smaller as he walk away from the lamppost. And this it makes sense because if he stand right here, his shadow could be the whole thing here, right? And then he walked up to here, his shadow gets shorter and shorter, and it's shorter by 1 meter per second. After we solve this problem, we realize that. So we pair the ratio, right? We say, we're gonna make the ratio small triangle over big triangle. So this is the small triangle involve the letter S, which is his shadow from here to here. So we say 2/5, which is this term, 2/5, equal this shadow over the whole length here, right? So his shadow over S plus 10 minus X. And we solve for the equation, we make it short. Now we make a derivative and we get the answer at the final. So I hope that you enjoyed the problem I went through with you. And you can see that each problem I show a different variety of problems. None of the problems are the same. So that's why I found like application. This chapter is really interesting. Now the next chapter, we still use the application, but we're talking about the sketching curve to find the maximum and minima. And then we still use the maxima and minima concept to solve the problem for the derivative. So stay tuned for that. See you in the next video. Thank you for watching. And if you like my work, please give me a thumb and hit subscribe. Don't forget to hit subscribe and give me a thumb to cheer my spirit up. Thank you, everyone. Thank you for watching. Bye for now.